Alright, so this trend, I'm going to go over electronegativity. Alright, so electronegativity basically is how electrons are attracted within a bond. So for example, if you have two atoms bonded together, now we have atom A bonded to atom B. The atom with the higher electronegativity is going to attract electrons more strongly. We're going to talk about this in a lot more detail in the next chapter, but I want to mention it here along with talking about periodic trends because it also applies. So the idea here is what atoms can attract electrons more strongly within a bond. You know, if atom B is stronger, it basically can pull electrons more strongly towards itself, because maybe B is the more electronegative element. I'll label the delta negative sign implying that's more negative. I'm going to label the A as delta positive implying more positive. We're going to see this again later in the semester. With respect to the trend, I'm going to leave the noble gases out. And this is going to follow the same idea, the same basic trend as electron affinity follows. It turns out fluorine is the most electronegative, and it turns out francium is the least. So this follows exactly the same pattern we see with electron affinity, but it says we have an increase left to right. So fluorine wants to attract electrons the most strongly. And it turns out going down the periodic table, I have a decrease. Decrease is going down. So fluorine is the most electronegative, francium is the least electronegative, and where we're going with this eventually in the next chapter, we're going to be able to be looking at electronegativity values. We're going to be able to figure out whether a bond is ionic, polar covalent, or non-polar covalent. It turns out if the difference in electronegativities is sufficiently large, is a big difference in values, if you subtract them, if that number is large enough, we're going to find that the bond will end up being ionic. So if atoms are farther, basically the rule is the farther atoms are apart in the periodic table, the more ionic the bond will be. Atoms which are close together, maybe we're talking about O with S, atoms are very close by, they will tend to either be polar covalent or non-polar covalent depending on the exact magnitudes of their electronegativity values. So for problems like these, I would give you numbers. For example, fluorine has a value of 4.0 and lithium is maybe sodium, I believe, is around 0.9, give or take. If I were to subtract those numbers, the difference ends up being 3.1. And if this number ends up being larger than 2, we're going to call it ionic. So if you see this on the exam, what I would do, I would give you a table that you can compare to, and all you have to do is subtract the numbers I give you, look at the table, and you can tell me if it's ionic, polar covalent, or non-polar covalent. Ionic means electrons are being totally stripped away from one atom, given to the other. We're going to have something with negative charge, something with positive charge, ionic substance. If it's polar covalent, you may have something like two nonmetals with very different electronegativity values. So maybe it's like carbon bonded to, say, chlorine. Electrons are going to be tugged very strongly towards the chlorine, for example. That would imply that this basically I end up with a partial negative charge and a partial positive charge. So that'd be like example of, say, polar covalent, where I have a charge disparity, but electrons are not completely transferred, they're sort of shifted to one side to the other. Non-polar covalent, we're talking about two atoms, maybe they're identical, maybe H bonded to H, electrons are going to be shared between them equally, you have equal sharing, there's no charge disparity, and the change, if you subtract the values, is really, really small, like something around like 0.1 or 0.2 or thereabouts. Again, I'll give you the table to illustrate this, but here electrons are shared equally between the two atoms, and there's no plus-minus business. So that's basically what we're going to use electronegativity for.